In 8 minutes, I'll quickly cover all the types of probability questions with high frequency in exams. There are 6 major types in total. We'll go from classical probability to mutually exclusive events, and from conditional probability to the 3 major distributions. After listening, you'll be a true master of probability. In 8 minutes, I'll take you through all the basic probability questions. They're all very simple. So after this lesson, every probability question will basically be a free point for you. Let's start with the first type, classical probability. What is its essence? It's actually enumeration. What the college entrance exam tests is enumeration. For example, 3 students are taking a sports test, and each of them needs to choose 2 out of 4 events to participate in. Then, what is the probability that exactly 2 people choose exactly the same events? Think about it. Of course, we need to calculate the numerator and denominator separately. What is the denominator? It's the total number of possible outcomes. The numerator is the number of outcomes that meet the requirements of the question. Let's first look at the denominator, which seems relatively simple. The denominator refers to the total number of possible outcomes. Think about it. For each student, they are choosing 2 out of 4 options. For the first student, they can freely choose any 2 out of 4. For the second student, it's also choosing 2 out of 4. And for the third student, again, it's choosing 2 out of 4. But when it comes to the numerator, think about it. Everyone. Now, the 2 people are choosing exactly the same items. All right, let's discuss these 2 people first. These 2 people are chosen from 3 people, selecting 2 to be the lucky ones together. So what about these 2 people? I still need to choose 2 items that are exactly the same from these 4 options, so we multiply by C42 again. Okay, we've already prepared for the first special element, and now we have only the last troublemaker left, the last kid. He says, hey, the items I choose can't be exactly the same as yours. Now, many students, when they get to this part, say, if I can't be exactly the same, I'll just do a case analysis. For example, if I'm one of them, one is different. For example, if I have 2 different ones, I split it into 2 cases to write it out. Slow down, okay? Since we only have 8 minutes, we need to speed up a bit. So how do we calculate this? We just gave an example. Can we try thinking about it in reverse? Think about it. Under normal circumstances, with no restrictions, I can freely choose any 2 out of the 4 items to do, right? But think carefully. Now I can't have the 2 of them be exactly the same. So if those 2 choose a certain combination, I have to eliminate that option and not choose it. So we directly use C42. Isn't it fine if we just eliminate that option? Right? So, once we've calculated both the numerator and the denominator, everyone can plug in the numbers, and the answer is 5/12, which is option C. Now let's look at the second question type, mutually independent events. Remember this, everyone. Mutual independence refers to what? It's a kind of independence in terms of calculation. As long as you can calculate that PA and B equals PA times PB, I don't care how much it doesn't make sense to you logically. If the calculation works out this way, then they are mutually independent. Do you understand? But what concept stands in contrast to this? It's mutual exclusivity. Mutual exclusivity is a judgment based on the meaning of the words in Chinese. It means that the 2 events cannot happen at the same time. That's what mutually exclusive events are. Now let's look at this problem. We roll 2 dice at the same time and shoot an arrow once. Let event A represent that the number showing on the first die is odd, event B represent that the number showing on the second die is even, and event C represent that the sum of the numbers showing on both dice is 6. So let's first write out our PA. For PA, since we're talking about the first die showing an odd number, we only need to look at the first die. Out of the 6 possible numbers, how many are odd? There are 3, 1, 3, and 5. So that's 3 out of 6, which is also 1/2. Now let's look at PB. Similarly, for the second die to show an even number, we only need to look at the second die. Among the 6 numbers, 2, 4, and 6 are even. So that's also 3 out of 6, or 1/2. Next, let's look at PC. For this, we need to use enumeration. All right. The sum of the numbers showing on the 2 dice is 6. In this case, let's count them. For example, 1 and 5 works. Here, the first number is 1, the second is 5. Then, can we write 2 and 4? That's also fine. 3 and 3 works as well because the first die can be 3 and the second die can also be 3. Next, 4 and 2 is possible and 5 and 1 is also possible. So when we write this as a fraction with numerator and denominator, there are 5 possibilities for the numerator. Now, consider the total possible outcomes. For the first die, there are 6 possibilities, and for the second die, there are also 6. So the probability is 5/36. All right, let's continue with our PD. For PD, it's the case where the sum of the two dice is 7. So let's keep listing them out. It could be 1 and 6, 2 and 5, then 3 and 4. What else? 4 and 3, then 5 and 2, and finally 6 and 1. So you'll notice that if we arrange the first number from smallest to largest, you won't make a mistake when writing them out. Let's count the total cases. There are 6, right? Our denominator is the total outcomes, 6 times 6, so the probability is 1/6. We've used all the problem's info. Now for the options. Option A says A and B are mutually exclusive, meaning they can't happen together. Event A is an odd first roll, B is an even second roll. Can they happen together? Does one affect the other? Think about it. A can happen with B, so option A is wrong. Now let's look at option B. It says that PCB is a conditional probability, so we must write it as, let's rearrange it. On top is PB and C, and on the bottom is PB. Let's see, our PB is 1/2, and as for PB and C, we definitely need to calculate it. That is, the probability that B and C happen at the same time. Event B is that the second die shows an even number, and event C is that the sum of the two dice is 6. So let's directly look for this within event C. When the second die shows an even number, this counts as 1, and this also counts as 1. So there are these two events. Now think about it, I have a total of 2 events. Our denominator is the probability of all possible events. How many total events are there? Isn't it 6 possible outcomes for the first roll and 6 for the second, making a total of 36 events? So the calculation comes out to 1/18, so we put that in, and the final result is 1/9. You see, option B is completely wrong. Now let's look at options C and D. What is C? Our events A and D are independent, so I just need to look at the probability of both A and D happening at the same time. For A, it's that the first die shows an odd number, and for D, the sum of the two dice facing up is 7, so we still need to look for this within event D. It requires an odd number, meaning the first die is odd, this one is okay, this one is okay, and this one is also okay. So there are a total of 3 events, and the total number of possible events is still 6 times 6, which is 36, so the probability is 1/12. Now, what about PA times PD? Isn't it 1/2 multiplied by 1/6? You'll notice, interestingly, that this is exactly equal to PA and D, so they must be independent. The answer is C. Don't worry about whether it makes sense to you logically. As long as you can calculate it, then they are independent events. Now let's look at our first option, option D. It says, what are events C and D? Are they mutually exclusive events? What are C and D? One is that the sum of the two dice is 6, and the other is that the sum is 7. They are definitely mutually exclusive, meaning they cannot happen at the same time. But being complementary is an even stronger relationship than being mutually exclusive. What does it mean to be complementary? Not only do the two events have to be mutually exclusive, but together they must also make up the entire sample space. Now think about it. We are definitely mutually exclusive, but do we really make up the entire sample space when combined? The sum of the two dice could be 8 or even 9, right? So when we add the two together, they do not make up the total event. Therefore, option D is definitely completely wrong. Choose C. Now let's look at the third question type. Conditional probability. From 9 numbers, 2 are drawn at random without replacement. Event A represents that the first number drawn is odd, and event B represents that the second number drawn is a multiple of 3. So what is PBA? First, you need to write this conditional probability as PA in the denominator and PA and B in the numerator. You must remember this. When dealing with conditional probability, always see it as a fraction with a numerator and denominator. Move the A to the denominator and then combine it with B to form the numerator. So now let's calculate P of A and B and P of A separately. P of A is definitely easier to calculate. It refers to the probability that we pick an odd number on the first draw. Out of the 9 numbers, there are 5 odd numbers. 1, 3, 5, 7, and 9. So P of A is simply picking one odd number out of 9, which is 5/9. Now let's look at what P of A and B is. P of A and B refers to both events happening at the same time. The first time we pick an odd number, and the second time we pick a multiple of 3. Now, which numbers are multiples of 3? That's 3, 6, and 9, right? But if you think about 3, 6, and 9, both 3 and 9 are also odd numbers, aren't they? So here we run into a problem. If we pick 3 on the first draw, then when we go to pick a multiple of 3 on the second draw, we're left with only 6 and 9 to choose from, which is a critical limitation. But if the first pick is from the remaining numbers, if we pick 5 or 7, these less significant numbers, on the first draw, then for the second draw, we can still choose from all 3 multiples of 3, right? That doesn't affect the probability. So at this point, we need to consider 2 different cases. The first case is, if things go well and we pick one of the good numbers like 1, 5, or 7 on the first draw. Now think about this. Out of the 9 numbers, the probability of randomly picking one of these 3 numbers is 3 out of 9. For the second draw, we pick from the remaining 3 numbers, 3, 6, and 9 at random. At this point, I need one more, and there are 8 numbers left. So from these 8 numbers, the probability of picking one of these 3 is 3 out of 8. That's how it works. But if, for example, the first number we pick is either 3 or 9, those odd-numbered positions, then out of the 9 numbers, these 2 numbers account for a probability of 2 out of 9. Now, for the second draw, let's just pick 1 at random. For instance, if we pick 3, then there are 8 numbers left, and among those 8, 6, and 9 remain. So, that's a probability of 2 eighths. Adding these two probabilities together gives us our PAB. After calculating, it comes out to 1370 seconds. Finally, let's substitute this in. The numerator is 1370 seconds and the denominator is 5/9. If we multiply both the numerator and denominator by 72, we get 13/40. So the answer is option B. Now let's look at question 4. It's about a binomial distribution. We define a random variable BB which follows a binomial distribution, and then, according to this diagram, it 5/9. Everyone, whenever you see greater than or equal to a certain number, you must list out all the possible cases. It could be equal to 1 or it could be equal to 2. You'll notice that if I calculate these two cases separately and then add them together to get 5/9, it's a bit slow. Since this class is being taught in the Peking University lecture hall, I definitely want to be a bit faster. So in this case, let's do it the other way around. We'll write it directly as, if it's less than 1, then it's 1 minus 5/9, which is a probability of 4/9, and being less than 1 is just one case, which is when it's 0, right? So everyone, take a look. What does this 2p mean? The 2 refers to how many times it occurred, and p refers to your probability of success. Here, I succeeded 0 times, which means I failed twice. The probability of failure is 1 minus p, so failing twice is 1 minus p squared, which equals the square root of 4/9. So 1 minus p equals 2/3, which means p equals 1/3. This question is actually quite simple because if I were the one making the question, I might ask about ex or dx. Everyone, make sure to remember this. For a binomial distribution, it looks like this. So as you know, when we want to calculate the expected value, it's equal to NP. And when we calculate the variance, it's NP times 1 minus P. These are formulas that cannot be changed. Now let's look at question 5, which is about the hypergeometric distribution. What does that refer to? It's like drawing balls. When I grab a handful of balls from a pile, how many of them are white? How many are black? And how many are red? This kind of scenario is what we call a hypergeometric distribution. Now, let's look at this problem. It says that a bag contains 10 black and white balls that are identical except for their color. So there are 2 types of balls. Let's suppose there are k black balls, then there are 10 minus k white balls. Let's continue. It is known that the probability of drawing at least 1 white ball when picking 2 balls from the bag is given. Whenever you see the word at least, you should immediately think of using the enumeration method. At least 1 white ball means either 1 white and 1 black, or 2 whites. Now, you don't need to foolishly calculate every possibility, right? Of course not. You should approach it from the opposite direction, right? What should I actually do? I should express it as, well, since I want at least 1 white ball, I can instead calculate the probability of getting 2 black balls. If it's 2 black balls, then the probability is 1 minus that, which is 2/9. Now, let's calculate the numerator and denominator. The denominator is the total number of possible outcomes, which is the number of ways to choose any 2 balls from 10. As for the black balls, that's our numerator, the number of ways to choose 2 balls from the black ones. So after calculating, it comes out to be 2/9. If we do the math ourselves, we find that k equals 5. Okay, so we don't need that condition anymore. We have 5 black balls and 5 white balls. Let's continue. Now, if we randomly draw 3 balls from the bag and let x be the number of white balls obtained, what is E of x? Remember, if the question asks for the distribution, I can't help you, because for the distribution, you need to calculate each case one by one. My x could be 0, 1, 2, or 3. I would have to write out all 4 cases, right? But if it only simply asks you for the expected value, let me tell you, the expectation for the hypergeometric distribution is very simple. Its expected value is also NP. However, its variance is a bit more complicated to remember, so I suggest you don't memorize it, just calculate it directly. But the expected value is tested very often and is easy to remember. It's NP. So in this case, what is our N? Isn't it 3 balls? And P, that is the probability of drawing a white ball out of the total, which is just the number, so 5 out of 10, which is also 1/2, multiplied by 1/2. So that's 3 halves. So this question is done. Now let's look at question 6. What is being tested in the normal distribution here? Students, it's the area, it's testing the area of symmetry and so on. First, let's look at x, which follows a binomial distribution. B here refers to the binomial distribution. As for y, it follows a normal distribution. Engine natural just means the standard normal distribution. Now, p of x less than or equal to 1 is equal to 0.36. Let's think about this. If p of x less than or equal to 1, since x is a binomial distribution, it could be 1 or 0. If I write out all the possibilities, it would take too long, so it's better to approach it from the opposite direction. So p of x greater than 1 would be 1 minus 0.36, which is 0.64, and greater than, in this case, p of x equals 2. That is, p of x equals 2, which means I succeeded twice. The probability of success is p, so the probability of succeeding twice is p squared, which equals 0.64. From this, we can deduce that our p is equal to 0.8. Okay, this is a useful condition. Now, for p of y less than 4, it equals 0.8. Let's draw our axis of symmetry here. This normal distribution has a mean of 2, so we mark 4 here. The area less than 4 is 0.8. So, the area on the right side is 0.2. Right? The right side is 0.2. We also know that the area on both sides of the axis of symmetry is exactly the same, which is 0.5. So this section is 0.5, and this section is 0.2, which means this section here is 0.3. Okay, now let's look at the last sentence. It says, what is p from 0 to 2? 0 to 2 means from 0 to 2, which is this section here. And we notice that 0 and 4 are symmetric about the axis at 2, so the area from 0 to 2 is the same as the area from 2 to 4. What is that value? It's our 0.3, so just choose option C. As long as you finish this lesson, you'll definitely be able to solve these types of problems.
You can be exactly the kind of person you want to be.
I've got 3 valuable resources for you. A 40-page guide with 100 problem-solving tips from Northwestern, my 20,000-word book on how I raised my math score to 146 and its core methods, and a free math analysis and study plan for the first 50 students. Join my pinned group chat to claim them. Achieving first place in math in your grade is never about talent. It's about following the right process. I'm Beta Tang. See you next time.